So welcome everyone to the Princeton Wireless Distinguished Seminar Series. It is my pleasure to introduce to you Shyam Gollakota from University of Washington. Shyam is a Tarot professor at the Paul Allen School of Computer Science and Engineering at UW. He works across multiple disciplines of the university, including computer science, electrical engineering, mechanical engineering, biology, and the School of Medicine. His work has led to 3 different startups, and he's also worked closely with the Washington Department of Agriculture to wirelessly track the murder hornets in the US. He is the recipient of many different awards, among them the NSF Career Award, a Sloan Fellowship, the Rockstar Award, the Grace Murray Hopper Award, and many, many others. And with that, I will let him take it away with his talk entitled Creating the Internet of Biological and Bio-Inspired Things. So welcome, Shyam, and whenever you're ready.
Thanks, Kyle. It's my pleasure to be here. And I'm excited to share about our work we have been working on for the last, I would say, 3 to 4 years on creating the Internet of biological and bio-inspired things. So if you think about nature from an engineering perspective, we notice that it does some really amazing things. For example, if you see something like a bee has enough stored energy to fly for hours. It has vision to navigate. It's very sensitive to smell, and it can process all this information on board in its brain. And it can do all this in a very tiny, power efficient, and lightweight package. In fact, if you look at something even simpler, like, for example, a dandelion tree, it can disperse seeds in the wind for over kilometers in the right conditions. So this is what nature can do. In contrast, if you look at what happens in terms of our the capabilities of current IoT and embedded systems, there's a pretty big gap between biological systems I just showed you and these IoT systems, which are much larger, heavier, and most cannot really move around. Imagine instead, if we can create tiny battery-free wireless devices that can move around and in fact float in the air similar to dandelion seeds. If we can do this, then we can deploy hundreds of these sensors in the wind in remote, hard-to-reach areas like forests and glaciers. In fact, if we can actually start designing wireless sensors that are so small, then we can also attach them to tiny insects like bees, beetles, and even murder hornets, and use them to understand the behavior of these kind of animals in the wild. This is actually important because unlike larger animals like zebras, which Princeton has done the most popular zebra net, the wildlife tracking of insects and small animals like birds has not been possible because they cannot really carry large batteries. In fact, we can take it one step further and we can integrate very low power actuators with wireless sensors and finally enable mobility for these kind of IoT devices. So we can introduce this new dimension, which people typically don't talk about for IoT devices, that is low power mobility, which allows us to sense things in confined spaces like pipes, under industrial equipment, and so on. So that's the vision. And what I'm going to talk about here is 3 specific systems we have designed over the last 3 to 4 years on creating what I call this Internet of biological and bio-inspired things. The first thing I'm going to talk about is how we created bio-inspired battery-free wireless sensors that can be dispersed in the wind across a large area similar to dandelion seeds. Second, I'm going to talk about how we created the Internet of biological things that we can use for wildlife tracking of small insects and animals like bees, murder hornets, and so on. And finally, I'm going to talk about how we can introduce mobility. And in fact, how I'm going to specifically talk about the smallest terrestrial robot that has steerable vision and which is completely wireless and it is power autonomous as well. So this is good. This is a roadmap for the talk. But one question you should be asking at this point is, what is the common enabling technology that enables all these kind of applications? And that specific, our approach to do all these things is to use programmable general purpose computing devices to build and create tiny wireless systems. And as I'm going to show you in a few minutes, this kind of an approach, which uses general purpose computers, which are widely available, allows for rapid prototyping and the scale of innovation that has not been possible for these tiny wireless devices. So I'm going to take a tiny detour here for 2 to 3 minutes and try to explain why creating tiny wireless systems is challenging. So the goal here is to create end-to-end systems, not to create just one component. And creating an end-to-end system at this kind of a scale requires us to have a computing platform to do digital processing. We need to have a wireless link like a radio to make sure that it can communicate. We can also basically need interfaces to interface with various kind of sensors. And finally, we need to have a power source to power all these different components. And the traditional way, which people have been doing and making small things, has been to build custom ICs. And as we all know, to a large extent, custom ICs have a high fabrication cost. They typically take multiple years of design cycle, and they're often built for a specific purpose, and they're hard to reuse. And the result of this is that only a few groups have the expertise and, more importantly, the resources to innovate in the space. And if you take a step back, it's actually similar to wireless research before the creation of software-defined radios, where effectively the fact that you had to create a custom radio IC was holding back a whole community of researchers. So what we show here is that we can create tiny wireless devices using programmable general purpose off-the-shelf components like microcontrollers and build millimeter scale wireless sensors. For example, the smallest commercial microcontroller you can buy on the market as of at least 6 months back is this tiny 1.5 by 1.4 millimeter microcontroller. It has very limited computation and actually does not support any kind of an interface to sensors, but it's programmable, which means that we can implement all kinds of different protocols like I2C to talk to sensors using just software. And while it does not have a radio either, later on I'm going to show you how we can use a technique called backscatter to create tiny battery-free wireless sensors that can use off-the-shelf components by just writing code on these computing platforms. So I think this actually is a pretty powerful approach because it eliminates the need to design custom ICs, at least for this specific application. And it empowers anyone who has a computer engineering background to build tiny wireless devices. And as a result, it has the potential to exponentially increase the pace of innovation across a range of domains, ranging from smart agriculture, biological tracking, micro robots, and implanted devices. So specifically, what I'm going to talk about here is how we can create this Internet of biological and bio-inspired things, which kind of spans 3 different disciplines: battery-free systems and wireless networking, microfabrication and actuation, and finally, an understanding of biology itself to integrate how these electronics can be integrated with these living systems. And I'm going to hopefully convince you at the end of the talk that taking this kind of an interdisciplinary approach allows us to create entirely new inventions and build innovative systems that push the boundaries of what's possible with technology and off-the-shelf components, honestly. So let's get into the meat of the talk. We're going to, as I mentioned, talk about 3 main systems over here. And so let's first talk about the first system, which is bio-inspired wireless sensors that can float in the wind like dandelion seeds. So to understand why we want to do this, here's a project which one of my ex-students has been working on with Microsoft Research, where they're trying to design low power air quality sensors and deploy hundreds of these things and deploy it in various zip codes across Chicago. But while they started deploying it, they started realizing that the task of sensor deployment itself requires sending a technician to each of these locations, which adds up a lot of time and money as well. In fact, there's the same problem you're going to see if you want to do large-scale sensor deployments on large farms to enable smart agriculture applications as well. In fact, there are also a lot of applications where the act of deploying the networks itself can be pretty dangerous and costly. For example, this video shows sensor deployed to monitor Mount St. Helens over here in Washington State. It requires a helicopter and highly trained professionals in dangerous situations to go and then place the sensors themselves. The same is also true for deploying sensors in the context of forest fires, which we are all too familiar on the West Coast. So this is the fact that we have to deploy sensors is actually pretty challenging. But if you remember, the dandelion seeds I showed you earlier have actually solved this problem. By just floating in the wind, they can travel for over a kilometer in the right conditions. So if you look a little closely at what's happening at a dandelion seed, it has this light, bristly structure at the top called the pappus that kind of acts like a parachute. And at the bottom, you have this denser seed. Now, when this thing starts falling, you're going to have a force of gravity pulling it down. And you're also going to have a drag resistance force, which is because of air, which is caused on this specific seed itself. When both these forces cancel each other out, you're going to stop accelerating and you're going to reach the terminal velocity. And the interesting thing over here is that the terminal velocity is dependent on the weight of this whole structure, as well as the area and a structure-dependent drag coefficient. So this is basically physics from your high school. But the main takeaway over here is that dandelion seeds evolved over millions of years to optimize both these parameters. They have a low weight and they also have a good drag, structure-dependent drag coefficient, and so on. So basically, motivated by this, we create one of the first battery-free wireless sensors that can be dispersed in the wind like dandelion seeds. It's kind of truly a systems work because it requires innovations at various different subcomponents, including designing wireless communication, power harvesting, and creating the structure itself so that you can minimize the terminal velocity and actually end up landing in the upright position. So I'm going to talk a little bit more about each of these technologies because I'm going to reuse these technologies for the other two systems as well. So let's first start with the first question, which is, how do we enable wireless connectivity at very low power and minimal components? So this is actually pretty challenging because radios typically require lots of power and external components. A typical radio has two main parts: a digital baseband processors at a high level and an analog radio front end. Over the last few decades, actually multiple decades, thanks to the Moore's law, what we have seen is that the power consumption of this digital baseband has come down significantly. However, we haven't seen a similar kind of a scaling for the analog front-end part. And as a result, what you see is that these radios consume significant more power than what we actually would want to have. So one way to reduce the power and the weight, in fact, is to outsource all the heavy and power-intensive components to a base station, a plugged-in base station, which already has power. And all you're going to do on these small devices is digital baseband operations. The cool thing about doing this kind of an outsourcing is that it allows us to abstract away the radio so that all we are using is programmable chips like microcontrollers on this tiny device, which means that you need just a microcontroller mostly to build these tiny devices, and you can implement your communication mostly by just writing code. And the way we do this kind of decoupling is by using a technique called backscatter communication. So at a high level, the way to think about it is that radios generate signal. Backscatter communication, in contrast, is communicating by reflecting signals which already exist in the wireless medium. So at a high level, if back in the day, people used to have mirrors and you can move the mirror and there's light coming in to send data. So it's kind of similar to that in this context where we're not using mirrors, but we're using similar reflections in the radio domain, not light, to enable communication on radio signals. So let's say we have a transmitting base station, which is generating the signal, and there is a receiving base station, which is also plugged in. So the way to think about it is that your transmitting base station is sending a simple sine wave at the specific frequency you want to transmit. And all you do at the small device is have basically connect a switch to an antenna, and you either connect the switch or disconnect the switch. And what that basically means is that you're changing the reflections as seen by the antenna when you're changing the impedance of the actual antenna. And what that means is the reflections as seen by the receiving base station is going to change. And therefore, by encoding information in this toggling on and off, you can effectively convey information to the receiving base station. So this is actually kind of nice because it does not really require generating radio signals of your own. And as a result, it can be orders of magnitude lower power consumption than a typical radio. And more importantly, all you need to implement this is a microcontroller connected to a switch. You already have a microcontroller to do the computing and to talk to sensors. So all you need to add is a switch and an antenna, and ta-da, you have wireless communication for you. It's not that straightforward, however, because you're using reflections to communicate, which are pretty weak compared to a normal radio signal. And in addition, your antennas are also really small, which means that the range of this kind of a design at this scale has traditionally been limited to 1 to 2 meters, which is not that great. So the question really is, how do you get longer ranges on these programmable battery-free devices? I'm not going to, because it's the general setting, I'm not going to go into the details, but there's a lot of coding involved and single sideband subcarrier modulation with techniques which you can find in our papers. But the high-level result is that we can design this whole thing using this microcontrollers and off-the-shelf components for only a 15 milligram sensor that can wirelessly transmit at ranges of up to 80 meters outdoors and achieve rates of around 4.8 kilobit per second. And you can in fact get a longer range of around 200 meters if you are willing to scale down your data rate as well. So that's at a high level how we achieve like communication on these tiny devices using just microcontrollers. So now that I showed you how to communicate, let's quickly talk a little bit about how we can power these devices. So one approach is to use batteries, and we don't use batteries here because recharging them is a painful exercise, and also the weight of most commercially available batteries is already 70 milligrams. So instead we use this tiny thin film gallium arsenide solar cells, which weigh only around 6 milligrams, but in bright sunlight can provide up to 6 milliwatts of power. That's good, but the problem with solar cells, which you all might who work with solar cells know, is that in the real world, the light levels vary a lot. And unless it's constantly bright and sunny, you would not get enough power to run continuously, and you can't get enough power in cloudy Seattle to power these devices because it's, at least at this time of the year, we typically don't have as much sun. So the typical way to solve this, which you all know about, is you add a capacitor to store enough energy over time. And then when you're charged up enough, then you can run your system briefly and go back to sleep and wait for the capacitor to recharge. But when we tried this, so what we noticed is that the microcontroller, like most other chips on the market today, draw a little bit more power when it's starting up. It's typically the case that when you're starting up these devices, they consume a little bit more power because there's a lot more work to be done than when it's doing the operation. So once we reach the voltage, once we actually turn on the microcontroller, it starts drawing power and the voltage dips back down and you have to turn off the microcontroller. And what this means is that you're stuck in this cycle where you're always trying to do startup and you never have enough power to start up and execute actual sensor code itself. So we address this problem by kind of creating this circuit, which actually has a feedback loop to keep the system on and get through the startup phase. I'm not going to go into the details here, but I just want to show you the actual results of what actually happens. Then we tested in a variety of light conditions, including overcast days in Seattle. We can see that it can start up and it can backscatter tens to hundreds of packets per minute across a range of different sunlight conditions as well. And more importantly, it can also do complete cold start, which means that in the night, if the power completely drains off, it can again boot up from zero power. It's actually a very hard problem if you're working on these kind of things. And we showed that our circuitry can actually do that even in overcast day, and it can also achieve cold start. So we built this whole system by assembling all these off-the-shelf components together on a flexible PCB material. And we folded up the material circuit so that all these components can stack on top of each other to be the same size as an actual dandelion seed. So in this figure, what you're seeing is that we integrate a variety of different sensors like temperature, humidity, and light. Although this microcontroller does not natively support interfacing with these sensors, we implemented the I2C protocol by ourselves in software so that we can interface with all these different sensors as well. So this is good. I kind of gave you a high-level description of how all the electronics are going to end up working. Now let's look at how we can enable it to float in the wind and allow it to land upright, because the solar cell is in the top. You want to make sure that when it lands, the solar cell actually ends up landing in the upright position. So if all you cared about is terminal velocity, clearly if you increase the surface area of something which is falling, it's going to have more air drag, which means that you're going to reduce the terminal velocity. But the problem with a solid disk like this, which is basically just a flat solid disk, is that it's not aerodynamically stable, which means that if you drop the surface, it's going to flip repeatedly, and we don't know which orientation it's going to end up landing in. In contrast, if you look at a dandelion seed, even if you drop it upside down, you can see that it's going to flip over in midair and always land in the same upright orientation because of the porous structure that allows some of the air to flow through. So if you do basically how the air dynamics actually ends up working, it allows it to basically flip over and also like reduce its terminal velocity. The problem is that compared to a 1 milligram dandelion seed, our payload is around 25 to 30 milligrams. So if we just mimic these bristles, then the structure is actually going to fall faster and it's going to bend inward. So you can see on the right that it's bending inward. To alleviate this concern, we add an outer ring to couple all these bristles together to make sure that we get the maximum drag possible and reduce its descent velocity. So if you put all these things together, we see that even if you drop the sensor in the upside down position, it's able to correct itself and land in the upright position, similar to a dandelion seed. In fact, when we did it over like hundreds and hundreds of times, and what we saw was that the percentage was around 95% of actually dropping in the right orientation. So the way we fabricate all these things is by using a laser micro machining here at UW. Where we use this UV laser that can cut features down to around 10 microns. And the material that I'm showing you is similar to what's used in flex PCBs. So in principle, we can easily scale up production and also integrate it with your electronics itself on the same PCB material as well. So here comes a good part. We get to play with drones and release things. So we release these sensors from this drone, which you can see here. The drone releases the sensor circled, so you can see it releasing the sensor. It's going to be in red, and it starts falling to the ground. Because of the way the camera is oriented, it's still traveling right now. It's going to drop at some point onto the ground when the circle stops moving. But it's kind of nice because even in this moderate wind conditions, we were able to travel up to hundreds of about like 100 meters over here, which is kind of nice. It was actually pretty challenging to track where the dandelion seeds went or even go to higher altitude, because these things are so small that we can't like see where they're going. So we had to limit it to like moderate breeze conditions, because if it's too fast or if the drone is higher, it's hard to really track where they're going because it's so light that it can just get carried away by the wind. But the most important thing is that I showed you a single dandelion seed being dandelion sensor being deployed over here. But the real power is because it's so lightweight, we can have lots and lots of them deployed using a single drone. So you can just drop thousands of them at the same time, and they're going to deploy across, for example, a farm. Of course, when you drop thousands of them, you don't want all of them to fall in the same exact spot. Otherwise, they're going to just clutter. So to prevent this, we again look at dandelion seeds for inspiration, because dandelion seeds vary the structure of individual seeds to allow some of them to land closer and others to travel farther. That's how nature's evolved dandelion plants, so that they can change the structure, or the way when they're being created, the structure is different, which allows some of them to fall closer, some of them to actually explode and go farther. So we take a similar approach and computationally vary the structure shape, in particular the diameter and the fill patterns, so that we can get a range of terminal velocities. And this allows us to create lots of sensors that travel different distances from the release point. So when we release around 20 of these things, we see that they can basically cover different distances in the direction of the wind itself. And one of the things which is very interesting here is that you can get even longer distances if you go to a higher altitude in terms of your drone, or if you work with windier conditions as well. So what I showed you here is that by making advances across different subcomponents, we can start building programmable systems, which are really pushing the boundaries of what's possible. And we are building end-to-end systems. In particular, the end-to-end system I showed you is how to disperse sensors in the wind, similar to dandelion seeds. So I'm going to stop at the end for questions. So I have almost 15 minutes at the end for questions. So I'll keep going on and continue to finish all the topics and then come back to questions. So what I talked about so far is wind dispersal, which is largely a one-time operation in terms of its mobility. So the next logical question is, how do you make these small IoT devices fly repeatedly? This brings us to the second system, which I'm going to talk about, which is the Internet of Biological Things, which is a mobile IoT platform. So to get mobility typically for IoT, you can just stick a sensor onto a drone. But the problem is that drones consume a lot of power and typically have a battery life of only 10 to 20 minutes. This is actually a really fundamental problem. For example, if you look at a DJI Phantom 3 drone, it consumes on the order of 100 watt or so just to basically fly. Propellers, in fact, become less efficient as you scale them down. So smaller drones can often fly for only 5 minutes or less. In fact, our group has also worked on the even smaller drones which mimic insects, like the UW RoboFly, which is even smaller, but it can barely lift off. So the key takeaway over here is that it's fundamentally hard to make something fly for a long time. So how do we get mobility which is more continuous for IoT devices? So our idea is, instead of using drones, we're going to leverage live insects to carry wireless sensors in places like farms. The way to think about it is that the bees are already flying around foraging for food, so they can also collect the sensor data and they can store it locally. And when they come back to the hive, we can upload the data to the access point. The compelling thing about this kind of an approach is that it's a bio-based solution, which means that it does not require any kind of a mechanical propulsion. And it allows us to focus on just the task of sensing and not actually the propulsion, which is a way more power-consuming task. Also, we can leverage the fact that bees are already introduced onto farms for pollination. And these animals can sense things about their environment and the health of the planet, which is very hard to do with our existing sensors. So before I get to techniques, I'm just going to show you a video of the whole system working on a live bumblebee, just carrying our wireless sensor platform. It's attached using a very small drop of glue to the specific insect itself. So the big challenge is, unlike a drone, you bees do not come with a remote control to control their motion. And in fact, I'm against controlling other sentient beings, so I'm not going to be exploring research where we're controlling the path of these insects. But others have explored controlling other insects for much larger insects like moths, but it's very challenging to do it for tinier insects like bees, which no one has shown that you can actually even control. So instead, what we do is take a different approach, which is to do opportunistic sensing. What that means is that since we are getting the flight for free, if our sensors can compute the location information, then they can record data whenever they get close to the point of interest. And if you have hundreds of these bees which are all going around and they each, the positions of them, they can compute their own locations. You can get the sensor information across a range of locations and times as all of these bees go out and they're all mobile. So what we need really is a self-localization approach similar to GPS. The problem with GPS is just like other radios, it's very power consuming. So we need something which can give you the location yourself at a very low power and low size, and it can do it similar to GPS, which is that you can self-localize yourself. So our solution effectively is used to, what can we do from a receiver perspective? It's basically to use a passive envelope detector circuit, which consumes almost zero power. The problem with this kind of an approach is that all you get is the amplitude of the signal. And those of you who have worked on localization know that if you just use amplitude or if you just use RSSI, your location information, localization accuracies are going to be pretty poor. So our solution instead is to use multiple antennas at the base station and change the amplitude at the B as a function of phase. So to put it differently, we can repeatedly beamform across a range of angles, and when the beam aligns with the B, you will get the maximum amplitude at the receiver, and that will give you the actual angle with respect to the first base station. And if you have two base stations, you can, 2 or 3 base stations, you can triangulate and find the 3D location of the actual B itself. This is at a very high level. So we implemented all these things in real time on an actual insect, and it's running in real time on the bee itself. And at a high level, when it's evaluated, we see that we could get an error of about 4 to 8 degrees in open field, even when the platform is actually moving. And there's a lot we have to do also to address multipath problem as well. But I want to give you the system level evaluation, which is that it stores up to 8,000 location and humidity sensor pairs on the storage, which is there on the device itself. It has a battery life of around 7 hours. And if you're sampling every 4 hours, 4 seconds, and it also has a very tiny battery, so it can do storage and so on. And when it comes back, we can recharge the battery using RF power within 6 hours, and the upload rate is around 1 kilobit per second. So what I showed you is 2 different systems. One of them is a dandelion seed where the weight restrictions are less than 30 milligrams. And here for bees, where the weight restriction is around 100 milligrams. Of course, there's a bigger range here. What if you can actually, does it from a design space perspective, you can also ask the question, what can you do if you can carry a little bit more weight? Let's say you can carry 150 milligrams. Can you do something better? So by just adding 50 milligrams, we can start carrying off-the-shelf chips that have significantly more memory and processing power than the device I just showed you. And you can also start incorporating actuators like the one here, which can be used to release the actual sensor itself. So here is a cute, neat system we designed where we can send a command and the sensor just dropped from the moth. So we send a wireless command, and whenever the moth reaches the right position, you can actually drop the sensor. You can release the sensor from the moth or the drone, and all these things. It's extremely low weight, and it's actually extremely low power as well. And this actuator works like a tiny door latch. So if you open it, you can airdrop the sensor from something like this insect. And all this technology was pretty useful last year when the first murder hornet were found here in Washington State. My group worked with my student, ex-student Vikram worked with the Washington Department of Agriculture to place these wireless tags on these live hornets so we can follow them back to their nest and figure out where the nests are and looking at this wireless signal strength values. there was a lot of tries. We tried this for 3 to 4 murder hornets, and every try which failed, there was an article on CNN saying how the Department of Agriculture failed to find the nest. But eventually, this technique allowed us to find the nest after 3 to 4 tries, and we found the nest. There's a lot of stories to tell about that, but it led to the destruction of the first hornet's nest in the United States last year in 2020. In the middle of all the pandemic, but it's good because this year they're able to use this technique, and they're empowered now with this tool to go and locate various kinds of nests in Washington state itself. Beyond just hornets, this technology is also powerful tools for environmental conservation. We're working with a variety of different groups for tracking moths, snails, birds, hummingbirds, and even like endangered tarantulas. And all this code is open source, so you can download it. And if you want to do it yourself and build on it, you can download everything here. So I just showed you the kind of things we can do when we combine electronics with biological systems, and how you can do all these things to enable mobility for IoT systems, as well as tracking invasive hornets. This is great, but all the sensors I just showed you are very simple, low rate and low bandwidth sensors like temperature and humidity. How much more can we push this tiny programmable devices to support slightly higher bandwidth applications, like, let's say, video? Can you support video? And that's what brings to the final project, which I'm going to quickly talk in 5 to 10 minutes, which is how do we create the first insect scale wireless steerable vision system? We're trying to create a vision system similar to your eye, and you want it to be extremely low power and a small form factor as well. So one approach which people can think of, and I'm talking about small form factors and so on, is to leverage advances in miniaturization made for smartphone cameras. This seems like an intuitive choice because these are very small sizes and can support megapixel resolution. But the problem is that processing and the energy requirements needed to support these cameras require powerful processors and prohibitively large batteries. In fact, this actually is a pretty fundamental issue you also see in nature. If you look at something like a fly, their visual system has lower resolution than humans, but for some of these species, it can take up to 13% of the body mass. Further, the retina of the blowfly itself consumes around 8% of its resting metabolism. So the energy cost to support the sensitive photoreceptors have led many of these insects to actually develop high visual acuity in only a very tiny retinal region, which actually we do in humans as well. When I'm focusing, I can focus a lot in one of the ranges, and everything else is kind of blurred out. So to balance this kind of a smaller visual field, insects, and in fact humans as well, have evolved their visual systems to independently move their head independent of their body. And what this means is that many of the insects and animals can move their visual system to expand the field of view by dynamically scanning or maintaining focus on a moving prey. This is in contrast to moving the whole body, where this kind of adaptation will allow you to gather more information, but in a very energy efficient manner. As you can see that this is moving its eye and it's collecting more information. So motivated by this, we developed a fully wireless, mechanically steerable insect scale vision system. On the left, you can see a steerable camera attached to the abdomen of a live darkling beetle. On the right, you see the smallest power autonomous terrestrial robot, which actually has a wireless steerable camera as well. So here are some specs. The camera can stream monochrome 160 by 120 video, and can stream between 1 to 5 frames per second, up to ranges of around 120 meters. And the total weight of this whole thing, in addition to the battery, which in addition to everything else, weighs around 240 milligrams. And as I mentioned earlier, we can also steer the whole camera to pan over a range of 60 degrees. And the way we do it is by using a piezoelectric effect. So the way piezoelectric effect works is that piezoelectric materials, when you apply voltage, they deform in one direction. And if you stack two piezo materials on either side of a rigid material like carbon fiber, then you can make an electrode that can actually bend. So here you can see that you can actually, if you apply very high voltage, then you can get the whole thing to move at a very in a very consistent manner. So we designed the whole architecture. We designed the boost converters to get this 200 volt voltages required for it to move. It's all power efficient and it's all within this tiny package. But I do want to show you some of the results for video streaming. On the left, I'm showing you the frame rate, which you can achieve as a function of distance. And as you can see that, as you'd expect, as the distance increases, you can only support lower and lower frame rates. On the right, you're going to see the battery life, which you can achieve using the battery we use at different frame rates, and also if you're actually moving your head itself. One thing which is very interesting, which we noted here, is that we could not perform any compression, even JPEG compression, on the sensor, on the microcontroller itself, because it's a very tiny microcontroller, and doing this kind of a computation can significantly reduce the frame rate, because the cost, the time it takes to even do JPEG compression on a single frame, forget about MPEG, you can't even do that. So we had to just stream raw video frames. So to demonstrate the benefits of this vision system, we also built the smallest power autonomous terrestrial robot, which actually has vision. It's based on 2 vibration motors that allows the robot to move forward. While people have used vibration motors in the past to move, what is interesting over here is that we actually optimize the power of these whole motors, and it means that we can actually get it down to speed, to power consumption of around 9 to 33 milliwatts, depending on the speed. And the most interesting thing for me, coming from a networking perspective, is that the power consumption to move this whole robot was between 9 to 33 milliwatts, depending on the speed. And it's similar in terms of power to maintaining an actual Bluetooth connection. And I don't know about you, but that blows my mind that you can move a whole thing for the same power as maintaining a Bluetooth connection. That's just incredible. So here we can actually see this whole robot navigating using wireless vision. You can see it's a low resolution video, but you can use the streaming to the smartphone. So it allows a human to steer the robot itself. In fact, we are now working on getting the completely automated and designing machine learning algorithms, which allow these insect scale robots to move using this very low resolution grainy videos as well. In addition to navigation, you can also use steerability to track the motion between robots to make sure that they're in sight of each other. Here is another small robot which is actually moving, and you can see that as it's moving, we are steering the camera so that it's always in the center of your vision, so you can continue to keep steering it. In fact, as you'd expect, decoupling this head motion from the body motion significantly reduces the power consumption. And in fact, it reduces the power consumption by 26 to 84 times, which is kind of similar to what you'd expect in nature as well. Here's a cool video of this whole thing being on top of on a beetle, which means that you can get a panoramic visual information, as you can see here, and you can use this in principle to understand the animal behavior in the wild as well. So what I showed you so far is how, by being inspired by biology, we can create a variety of different systems, ranging from sensors that can float in the air like dandelion seeds, integrating these tiny sensors with biological insects, as well as creating steerable wireless vision systems, which kind of imitate how your head motion and eyes move to collect information. So if you take a step back, however, you can see that by working across designing these 3 different domains: battery-free systems and wireless networking, microfabrication actuation, biological systems, we can actually do a lot of interesting things using general purpose computing platforms at this very tiny scale. And what brings all of them together is a curiosity about biological systems. And I'm not saying that biology answers all our questions. In fact, it might not be the right approach for many problems, but there's so many things nature can do better than electronics and that we can learn from. So if we start thinking about this in this particular interdisciplinary manner, it can lead to a lot of innovations. I really believe that in the next 5 to 10 years, we can see a different way of thinking in wireless and embedded systems, which basically merges all these different domains. So to conclude, I'm excited about the future of biology and programmable wireless systems and embedded systems. In particular, I think the vision for the next 10 years is basically to merge this gap between these the IoT devices we have today and what biology can do. And there is so many things to explore here. You can start exploring intelligence. You can start exploring embedded, low-powered embedded ML, mobility. You can start talking about programmable swarms of these IoT devices. You can also start talking about integrating it even better with biology. For example, some of these insects can smell much better than any kind of a sensor we can create. So how about we just tap into the insect's sensing capabilities itself so that we can actually do a much better job of sensing. So it will be a truly bionic system where you're integrating sensors with biology itself. I do want to conclude by acknowledging some of my collaborators, including my ex-student, Vikram. He was on the job market last year and he did really well. He had offers from CMU and UW and other places, and he decided to stay at UW as a faculty. So next time you can interview him instead of, not interview, sorry, I meant like you can invite him so that he can give the talk instead of me. Thank you so much, and I'm happy to take any questions.
Thank you, Shyam. That was an amazing talk. I really enjoyed it, and I think you're really opening up a brand new area. So I want to invite everyone to put some questions into the chat. And if you can't find the chat, go ahead and raise your hand virtually in Zoom. And I'm sure we're going to have a bunch of questions. We have a good 10 minutes. I'm going to start out with something urgent that was on my mind, a question for Shyam. So I think my question is the following. So, the conventional wisdom of ASIC is that it's application specific, and therefore conventional wisdom is it's always going to be lower power because the circuit is designed, right? This is the conventional thinking. So is there a plot that you might have the plot, or you could kind of give us a sense? Can we plot like flops versus power versus weight over the years? And is something changing? Is general purpose microprocessors becoming light enough and power efficient enough to? I mean, obviously they can satisfy all your requirements, but is there something fundamentally, like, can we make sense of something fundamental that's shifting in ASIC design, I suppose?
So I don't have the plot with me on hand, but Josh actually created this plot. Josh is one of my collaborators here at UW, where he created the plot of the capabilities of microcontrollers in the last 20 years. And they are significantly improving in terms of their power consumption for sure. He hasn't plotted it for weight. But one of the things from our own experience building, we started off almost 10 years back building ambient backscatter. And these were like really big devices. It was built with off-the-shelf components. And one of the things, I'm in computer science and engineering department, so I like to innovate fast. And things are much faster, which means that creating an IC is not a thing which we can, it takes much longer space than what the students are willing to basically spend their time on, at least in our department. So when we started off, it was very clear that like we couldn't do things at the small scale 10 years back. And the things which changed, I've seen a pretty significant change in terms of the power consumption of microcontrollers, as well as the size of them. This microcontroller, which I just talked about, only existed like 3 or 4 years back, which didn't exist 10 years back. So they're not only getting more power efficient, they're also significantly reducing in their size, which is why I think there are a lot of applications where you can start working on right now, which would allow you to basically start building these things. That said, I don't think this is the only approach which is needed to be taken. In fact, we are exploring some other ICs in particular for video streaming, like the fact that we couldn't even do any kind of a JPEG compression or like even MPEG compression is pretty limiting. On a microcontroller. But if you could design a JPEG chip, for example, or MPEG chip, you can probably get a much lower power and start doing applications. So we are exploring that opportunity as well. But one thing we are still trying to avoid is trying to create ICs. And one of the things we're doing now is, okay, so we can create an MPEG chip or we can create a JPEG chip, but what if we don't actually do it and use machine learning instead or deep learning instead to try to do decompression, do something really, really dumb at the microcontroller level, which is you're just sending raw, low resolution videos. Maybe you can do super resolution. Maybe you can just send hints of colors and you can get high resolution color despite not doing a lot of compression on the chip itself. So there's a lot to be done here. If the solution is not always go create a chip, you can start thinking about integrating neural networks and so on at the power intensive side to come up with creative solutions, I think.
Yeah, like taking that asymmetric backscatter concept and applying it to computing itself. So
exactly.
Again, yeah.
I think that's one of the projects which we're actually exploring right now. Not to plug a project which is not yet published, but like one of the things we're doing right now is let's keep this. This is kind of like having dumb terminals, right? We used to do this in like distributed systems as well. Back in the day, you have dumb terminals and the processing is happening at the mainframes. Maybe these microcontrollers, maybe these IoT devices, all they're doing is dumb capturing of sensor, very, very low resolution video. And every so often it basically captures like a high resolution video frame. And you send all of these things to, without a lot of compression, to the base station. And the base station uses the magic of neural networks to reconstruct like a higher resolution video. So that's just one example of how you can think creatively without being limited. For a lot of time for computing, the always solution is, oh, we can't build ICs. It's not a thing which we do. But I think with neural networks and other approaches, we can come up with creative ways of solving the same problem, maybe even better than creating an actual IC on the low power device.
Yeah, when you say JPEG, like there's definitely like an ASIC that's maybe public domain, I'm not sure, but there's definitely like an ASIC for JPEG or MPEG, right? So like, have you thought also about integrating the general purpose with something kind of off the shelf yet application specific?
Exactly. So there were off-the-shelf components, but if it depends on how creatively you're trying to find the frames. For example, if the ICs which we found online for some of these video applications, they are very specific to a specific frame rate and a resolution. Like they work really well. They're optimized in terms of power for a specific frame rate of say 30 frames per second at a resolution of HD, for example. Let's say I don't want to do that. I want to send like a video which is at lower resolution because I want the other endpoint, the power intensive device to do most of the computing. Then maybe I can't, turning on an HD camera all the time is pretty power consuming, let alone the computation and the JPEG computation. So what if I don't want MPEG computation? Let's say I don't want to turn on the camera all the time, the high resolution camera. I just want to turn the low resolution camera. I just want to periodically turn on the high resolution camera and just send that one frame every 2 seconds to the base station. So you can't use off-the-shelf components in a power optimal way for this because they are not designed for low resolution video or low resolution frame rates. So it's a little bit more challenging, I think.
Gotcha. Okay. I think I saw Yaseman. Go ahead. And then we have a question from June in the chat after Yaseman.
Thanks, Shyam, for the wonderful talk and for accepting our invitation. So you talked about pushing the boundaries of low power IoT. I want to know your take on sort of future gigabit per second IoT that probably has to use like higher frequencies like millwave for communication. Where do you see that going in the future?
I think your work on it is pretty amazing in that domain. You're working a lot of very, very high frequency communication at very high data rate. I think that right now, millimeter wave and higher frequencies are still power intensive and they're still in the research phase. Millimeter wave a little bit less in research phase. So they are at this point for more powered devices or plugged in devices, if you might say so. I think the whole space of trying to design higher bandwidth things at this low resolution, at this much lower power. We're talking about battery free, or talking about like a single coin cell battery to operate a millimeter wave radio. I think it's a completely open challenge. People haven't really done a lot of work in it. You can try to think about backscatter for some of these frequencies, or trying to even optimize the radio front end at these frequencies so that it can be battery free. I think, yeah, that's the whole area which you can do. That said, I think we should also think about what applications for IoT would require, assuming you can do it, assuming you can get like gigabit per second speeds, what applications for IoT would require very, very low power and also very high resolution. So I think that is the thing we need to think a little bit about before we frame and start working on extremely low power. But in general, my take is, if you reduce the power consumption of communication, it's going to have applications, whether it's an IoT or even your radio. You don't want your radio to be super power consuming on your phone either. So power consumption is a solution, whether it's for IoT or even for typical phones as well.
Great. June, do you want to unmute and ask your question? Or I'll read it if not convenient. Okay, so I'll go ahead and read out June's question. So June is asking about the non-technical challenges with this line of research. Was it the IRB because you're working with living organisms, interdisciplinary research in general, and if somebody wants to start this kind of research, do you have any advice for them?
So I think the biggest challenge is actually having an open mind. I think this kind of research is extremely challenging, and as an advisor, when I went in with my students, particularly Vikram, I did not know anything about biology. I did not know anything about like insects or like what the real problems are. So having someone to tango with who is basically having an open mind and willing to like explore and fail, that is, I think, the biggest challenge. I think a lot of you on this domain have done similar things in your own domains where you went into new areas and open them up. So I think that is, one of the big challenges. In terms of IRB, for insects, you don't need to get an IRB. It's a different standard in contrast to animals. But at the same time, we need to know how to humanely handle insects and make sure that they're being fed properly, which is why we work very closely with biologists here at UW to understand what's happening and how to make sure that they are being well fed, they're taken care of well, we don't put too much weight. So biologists have a lot of understanding of a lot of questions we're asking here in terms of what can insects carry, for example. And that is information we can get from talking to them.
Yeah, that's my advice I give to new and prospective grad students is exactly what you said, Shyam. To have an open mind is one of the most powerful things in research. If Sophia, if you want to unmute, or I will read your question, whichever is faster or more convenient. So I'll go ahead and read. So Sophia Yu is asking, really cool work. I was curious about how battery charging was performed, whether the devices were individually removed from insects for charging, or if there was some charging station that insects would dock at.
So for the living IoT, we had an RF harvesting circuitry, which means that when it's back to the nest, we can send radio signals and charge the battery. It's a chargeable battery. It's a rechargeable battery, which means that we can recharge the battery, and it's a little bit less efficient because radio signals at that range, at even close ranges, because it's sending all directions, is inefficient. But we could recharge the whole battery wirelessly within 6 hours. So the way to think about it is that it's done with the day, comes back home, which is basically its nest, and when it's in the nest overnight, we can recharge the battery without docking it or anything. It's all wireless.
I'm just curious. We have time for one more question, but while we're getting that, one or two more questions. But I'm just curious if you ever considered, with the live insects, or instead, did you ever consider helium or gas or lighter than air gas to solve this problem you had with weight and flying for long periods of time?
What do you mean by gas?
So something like a balloon to fly to hover continuously.
So that is definitely something which we are considering right now. The problem is steerability. Balloons, I think basically balloon idea is what led to the dandelion seed, because at the smaller the scale you go to, what kind of a structure is more efficient to get wind dispersal. It turns out that the dandelion structure is more, so it depends on what sizes you're. If you're a larger size, a balloon is probably better. If you go to even smaller sizes, other structures are more efficient in terms of wind dispersal. That said, we are looking at some approaches for using maybe smaller balloons to achieve, you can get like these sensors to be deployed similar to what the Google people have done, but much smaller balloons. The challenge is, of course, controlling them, which is actually a really hard problem, controlling them to not just get just flown away. And I think that is the problem we're trying to solve right now. So like, how do you even like control them in a low power manner, but and in a smaller size so that it can carry a little bit more payload, but you can still make it not just go with the wind, and just like you can have it at least be in the same area of interest, for example.
Okay, and then in the 2 seconds we have left, we have this late-breaking follow-up question. Can we use atomic batteries in this device for more efficiency in charging? So same, I guess, same kind of area of power by, I'm not sure, by atomic, if the questioner means something technical with batteries or something else, but your thoughts on that?
Yeah, I don't know what atomic batteries are, but if you have, that's batteries are like the biggest challenge we have. So if you have a battery prototype which is small and which is better than the commercial batteries we have now, I would be more than happy to collaborate with you, because that is one of the biggest challenges in this whole line of research. The commercial batteries just consume like 70 milligrams, which is the biggest weight killer. So if you have some form of battery, please reach out to me. We can collaborate and design really awesome systems.
All right, and with that, I think we're out of time. So I want to thank you all. Thank Shyam for this talk. I really enjoyed it, and thank you all for attending. And goodbye and good day.
Thank you so much.
Thank you.